Welcome back to the last week of this course. In week 7, you saw the various PV system components and their characteristics. Now, we will see how these components come together and make up a PV system. In doing so, we will not only look at the characteristics of these PV systems, but also look at some of their basic design rules. We will first start with the standalone PV system. It is also called the off-grid PV system, simply because it functions independent of the electric grid. As discussed before, the standalone PV system has these important PV system components. The PV array is an interconnection of modules that supplies the required photo-generated power to the system. The power rating of the array is determined based on the load requirements. The battery bank is the lifeline of the standalone PV system, as it greatly increases the usability of the PV system. Without the battery, the system would be unable to meet the load demands outside the available daylight. As discussed last week, the charge controller is single-handedly responsible for assuring the smooth functioning of the battery. Given the complexity of the functioning of a battery, the use of a good charge controller can increase the lifetime of the battery manifold. This is more than welcome, as the battery is often the biggest bottleneck in a standalone PV system's lifetime. The standalone inverter has to be responsible for efficient power conversion from DC to AC power over a wide range of the loads. The better the inverter, the higher the efficiency over a variety of loads. Together, the charge controller, battery, inverter, distribution panels and the wiring make up the balance of system. In general, everything in the PV system minus the PV array constitutes the balance of systems, or BOS. The system could be connected to both DC and AC loads. Of course, the DC loads would be powered by the DC power before the inversion stage. Now, let us look at the features of such a PV system. If such a system is used to feed loads that are powered on at different parts of the day, how will the system cope with such a power demand? What happens when the PV array is producing more power than the load demand? Let us understand this using a simple animation. On a normal day with the sun out, the PV modules on top of this rooftop are busy converting the incoming irradiance into photo-generated power. The battery is constantly being charged or discharged through the charge controller, depending on the difference between PV supply and load demand. The off-grid or standalone inverter is continuously converting the DC power to AC and supplying this AC power to the loads. The system is designed and sized such that during the day, with the sun shining, the system generates enough power to at least meet the load demand for the rest of the day. Therefore, the PV system acts such that the battery is net charged over the day. After daylight, the rest of the power demand is fulfilled by the battery. Now, you might be thinking, what happens if it's not a sunny day? Or even worse, there's a string of dark days, like in many parts of the world. In such a case, if you have to meet the load demand, then there is no option but to oversize the battery so that the expected days of autonomy can be dealt with. Now let's go on to the more interesting aspect of designing an off-grid system for a house in a remote location. We shall look at the designing and sizing of a PV system based on the load demands and the available components. Let's go to this example. I will introduce you to a simple flowchart that helps to design an off-grid PV system. We will walk through all the stages of this flowchart while considering an example. Let us first define the load demand that has to be powered with an off-grid PV system. The total days of autonomy required should also be specified. Consider a house that is to be powered independent of the electric grid by means of a standalone PV system. Let's assume that three simple kinds of loads are required to be powered: light, TV, and desktop computer. The lights are supposed to be DC powered, while the TV and the desktop computer are AC powered. The required quantities of each kind of load, along with the duration of usage, are also mentioned. The total power and energy requirements have been tabulated here as well. Both the DC loads and the AC loads require a total energy of 300 watt-hours each per day. It is required that the system enjoys a total autonomy of 2 days. That is, a fully charged battery should be able to feed the load when there are 2 days without solar power. Now, we must account for the various losses in the system. In doing so, we want to estimate the minimum power that the PV array is expected to deliver. Here, we have the various efficiencies of the system components mentioned. The inverter is supposed to have an efficiency of 90%, while the combined efficiency of the charge controller, battery and cables is 85%. First, we have the DC and AC load energy required. Now, we must transpose these energy needs to the input of the inverter. The DC load energy remains unchanged, while the AC load energy is changed into the equivalent DC load energy based on the inverter efficiency as shown. Now, these equivalent load energies should be transposed again to the output of the PV array. This is so that we can get the actual amount of PV energy expected by the system per day. Again, we arrive at this total energy need by using the combined efficiency of charge controller, battery and the cables as shown. This is calculated to be 745 watt-hours. Thus, the PV array on a regular day should be able to supply 745 watt-hours of photo-generated energy. The next thing we have to consider is the equivalent sun hours. This will, of course, depend on the irradiance that the chosen location enjoys. In this example, suppose that the place is in a location within India and that the place enjoys an average of 4.5 equivalent sun hours. Knowing the load demanded at the PV output and the equivalent sun hours, we must now estimate the rated PV power required in the PV system. We have been given a particular type of PV panel that has the electrical parameters as shown. The panel is rated at 100 watt peak. Assuming that the panel would be operated at its maximum power point, we can find out the required number of panels as follows. We can first calculate the amount of minimum PV power required by dividing the total energy demand at the PV output with the equivalent sun hours. This gives us a power of 165.6 watt. Also, the number of panels could be calculated as shown, which in this case is found to be 2, as the number of panels would always be the upper approximation to a whole number. Now let us look at the possible PV configurations. The maximum allowable current and voltage rating can be found by assuming these scenarios. If the two panels are connected in parallel, then a maximum current of 2 times the short circuit current is possible, which in this case is 14 amps. On the other hand, if the two panels are connected in series, then a maximum voltage of 2 times the open circuit voltage is possible, which will equal 40 volts. Now, let's look at the specification of an available charge controller. In this case, we need to ensure that the charge controller parameters would conform with the maximum parameters found in the different PV configurations. The operational voltage is the battery voltage that is supported by the controller. It is also the voltage at which the DC side of the PV system would operate. In other words, the DC loads would be operated at this voltage. Thus, the nominal operating DC voltage of the system is dictated by the load rating as well as the battery bank. In this case, it is given as 24 volts. This is not to be confused with the maximum voltage, which simply specifies the amount of maximum voltage as provided by the PV output that the charge controller can handle at the input. We see that the maximum allowable voltage is greater than the series limit of the two panels of 40 volts. While the maximum current doesn't support the parallel configuration current of 14 amps. So we select the series configuration of the panels. In general, given a choice between series and parallel, series configuration is preferred to keep the current levels down, thereby minimizing the DC cable loss. Now, let's move on to the battery design. The battery size is greatly affected by the days of autonomous operation expected from the system. A single battery is given with the specifications as shown. The depth of discharge, or the DOD, is the depth until which the battery can be effectively used. We must now choose how the battery bank must be configured. That is, how many batteries of the given specification should be there in the battery bank, and how should they be interconnected. The minimum battery capacity can be derived as follows. Based on the operational voltage, depth of discharge, and energy demand, the battery capacity can be sized as follows. Note that the days of autonomy and the system losses tend to increase the battery bank size. Also, note that the lower the battery depth of discharge, the higher the battery bank capacity requirement. On the other hand, the higher the battery depth of discharge, the battery can be discharged more and therefore lower the battery bank capacity needed. So this gives us a minimum battery capacity of 103.5 amp hours. Now, this brings us to the number of batteries required. An operational voltage of 24 volts requires two batteries of 12 volts each in series, whereas a battery capacity of 103.5 amp hours requires 5 batteries in parallel. Therefore, a total of 10 batteries are required to create the battery bank for the PV system. Lastly, we come to the inverter sizing. Based on the efficiency of the inverter, the power rating of the inverter needs to be calculated. An inverter is available with an efficiency of 90% and operational voltage of 24 volts. What should be the minimum nominal power rating of this inverter? We know that the power demand of the AC load is 200 watts. Given the rated efficiency of the inverter, we can estimate the minimum nominal power rating as 222.2 watts. Note that the inverter may be less efficient than the rated efficiency, and under such conditions it may be safer to have a margin for the power ratings of the inverter. So we have seen a simple method to design a standalone PV system based on the load requirements and available system components. Note that this is definitely not the most exhaustive way to design the PV system. This method works better for places with a more or less consistent irradiance levels. For places with severe disparity between the summer and winter irradiances, the number of autonomous days would increase for winter and the system cost would consequently rise. Also, The components margins considered for various parameters could differ from place to place based on the system requirements. Nonetheless, this method is good enough to get a basic estimate of the standalone PV system sizing. You will be able to practice more on this in the exercises of this week. See you in the next blog. Welcome back. In the previous blog you learned about the standalone PV system and its design. Now we will look at the characteristics of a grid-connected PV system. So let's get started. As the name suggests, the grid-connected PV system is connected to the electric grid. There is a continuous exchange of power with the electric grid via the distribution panel. As discussed before, the grid-connected PV system has these important PV system components. The PV array is an interconnection of modules that supplies the required photo-generated power to the system. The power rating of the array is determined based on the system design. The grid-connected or grid-tied inverter is the backbone of the grid-connected PV system. As discussed last week, it is the inverter that is responsible for not only supplying power to the grid as a current source, but also for tracking the grid voltage and frequency. The grid and the load are usually connected through a distribution panel. The interaction with the grid is two-way, while the interaction with the load is unidirectional. A net meter is also usually found in this type of PV system. A net meter is nothing but a two-way power measuring instrument. This meter takes into account not only the power consumed from the grid by the consumer, but also the power fed to the grid by the PV system. Now, let us look at the main features of such a PV system. What happens when the PV array is producing more power than the load demand? And what if the PV power is insufficient to power the load? Let us understand this in the following animation. On a normal day with the sun out, the PV modules on top of this rooftop are busy converting the incoming irradiance into photo-generated power. The grid-connected solar inverters used in the system are also constantly converting the DC output of the solar modules into usable AC power. The PV system is able to meet the load demand of the household. On a different day, if it's a very sunny day, the PV system is providing much higher power than what the load needs. Under such a condition, the net surplus power is fed to the grid. In most countries, the consumer can offset his electric bills in this manner. This facility is called net metering. You can see that the net meter is reading a net production as the net power is being fed to the grid. On the other hand, on a cloudy day, the PV system is providing less power than what the load is expecting. Under such a condition, the load demand is fulfilled by taking the excess power from the grid. Thus, the net meter registers a net consumption as well. Now, we will look at the important concept of system efficiency. We know that the PV modules could be as much as 20% efficient in converting the incoming irradiance into PV power. We have also seen how the rest of the system components have less than 100% efficiencies. So what can be said about the overall system efficiency? In this grid-connected PV system schematic, you see the various system components. Let's walk through the system to see the efficiency loss at each stage. I will suppose some efficiency values for each component so that we can get a rough estimate of how the system efficiency might look like. Let's assume an AM1.5 irradiance levels and that the PV array is 20% efficient. Therefore, the power density present at the output of the PV array is 200 watts per square meters. as the balance of system could be placed at a considerable distance from the PV array due to the fact that inverters need to be well protected, it might be that the DC power loss in the cables is significant. Depending on the length of the cables and the amount of current through them, this loss could be anywhere around 1 to 5%. In this example, let's assume that we have a cable loss equal to 2% of the PV power production, or equivalently, the cables have a transmission efficiency of 98%. Therefore, the DC power per area going to the inverters is 98% of 200, which is 196 watt per square meters. Now let's go to the inverter. With advancement in power electronics, it is rather common to have inverters that reach greater than 97% efficiency. However, usually the efficiency of the inverter is dependent on the power at which it operates. It is seen from practice that the inverters typically reach their rated efficiencies at around 50% of the rated operating power. For the sake of simplicity, we shall assume an average efficiency of 95% for the inverter. Thus, the AC power per area present in the system is 95% of 196, which is 186.2 watts per square meters. Assuming a lossless exchange at the distribution panel and negligible dissipation in the cables carrying AC power, we get an overall PV system output as 186.2 watts per square meters. This means that the incoming irradiance at 1000 watts per square meters is processed by the PV system to give 186.2 watts per square meters. In other words, the overall system efficiency is 186.2 divided by 1000 watts per square meter, which is 18.62%. It can also be said that the overall system efficiency is calculated as the product of the various component efficiencies. That is, eta system equals eta PV times eta cable times eta inverter. Now, let us move on to the design of a simple grid-connected PV system. As a quick recap, let us look back at the flowchart of the standalone PV system design process. You will remember that the system design process had several steps. Given that the grid-connected PV system topology is significantly different than that of the standalone PV system, how does the flowchart of the grid-connected PV system differs from the standalone system design? As expected, the grid-connected system design flowchart looks simpler, owing to the absence of the battery and the charge controller. Although the load demand and the equivalent sun hours could shape the sizing of a grid-connected PV system, it is not necessary to base the grid-connected system sizing on the load. I will come back to this later. However, for this example, to get a sense of comparison with the standalone PV system design, we shall consider the grid-connected system design process with a load demand. In this design process, we shall first understand the load requirements from the system on a per-day basis. Then, we shall account for the system losses. We will then take into account the equivalent sun hours. Then, we will size the PV array. And finally, we will look at the inverter design. So, let's get started. Let us consider a similar load demand as shown in the standalone PV system design example of the previous block. The required quantities of each kind of load, along with the duration of usage, are mentioned. Note that all the loads in this system are AC loads. The total power and energy requirements have been tabulated here as well. Another main difference here is that there is no concept of autonomous days, as there is no storage. Instead, the electric grid acts as a limitless storage. Let us first account for the losses in the system. This would help us find the energy needed at the output of the PV array to successfully cover the daily load. Here, we assume the same component efficiencies as we saw in the earlier example. That is, the cables have a transmission efficiency of 98% for the DC power, and the grid-tied inverter shows an efficiency of 95%. We also see that the AC load at the inverter end demands a total of 600 watt-hours during the day. Given the system component efficiency, we can then calculate the equivalent energy required from the PV panels as shown. This is basically nothing but the transposition of the energy before all these losses occur. Therefore, the total energy requirement for the PV array is 644.5 watt-hours. Next, we consider the irradiance. Going by the same example as in the standalone system case, a location in India is considered with an average of 4.5 equivalent sun hours. Let's look at the electrical specification of an available PV module. It's a 100 watt-peak rated module with the given voltage and current parameters. Now, we need to find out how many of such modules are required to power the loads. Assuming that the panel will be operated at its maximum power point, we can find out the required number of panels as follows. We can first calculate the amount of minimum PV power required by dividing the total energy demand at the PV array output with the equivalent sun hours. Thus, the minimum PV power required is 143.2 watts. Also, the number of the panels could be calculated as shown. In this case, the total number of required panels is 2. Usually, panels are connected based on their compatibility with the DC ratings of the inverter. Care should be taken that the worst case current and voltage from the PV array do not violate the input parameters of the inverter. Now, let us look at the possible PV configurations. The maximum allowable current and voltage rating can be found by assuming these scenarios. If the two panels are connected in parallel, then a maximum current of 2 times the short circuit current is possible, which in this case is 14 amps. On the other hand, if the two panels are connected in series, then a maximum voltage of 2 times the open circuit voltage is possible, which will equal 40 volts. Now, I must clarify one thing about the grid-connected PV system. Usually, the amount of PV panels or the rating of PV panels need not be exactly as per the load requirements, like it was in the standalone PV system. This is because any excess or deficit of PV power can be compensated by the grid that is present in the scenario anyway. This was not true for the standalone system, as any surplus or deficit of power had to be met with a variation in the storage size, leading to considerable system costs. Consequently, in grid-connected PV system, it is usually seen that the inverter is sized based on the PV array sizes and not the load size, like in the standalone systems. So the required PV power is 200 watts. The inverter should be able to at least handle this power. Thus, we say that the minimal nominal rating of the inverter is 200 watts. Let us look at the operational parameters of an example inverter that fits the bill with respect to the required minimum power rating. Note that this inverter has a maximum power point tracking feature, thereby making the panels work at maximum power point. Looking at the IV ratings of the DC side of the inverter, we see that the maximum DC input voltage for the inverter is greater than the maximum voltage. On the other hand, the maximum DC input current for the inverters is less than the maximum current, but greater than the short circuit current. Thus we can say that the ideal panel configuration could be in series. Note that in practice, sizing of the system is not the only thing. One must take into account technical and regulatory policies before implementing a grid-connected PV system. In this video, due to time constraints, we limit ourselves with the sizing of simple grid-connected PV systems only. As a final note, I like to talk about oversizing the PV system sizing. Now, should or can a user oversize the PV system, even if he can meet the load needs for much lesser power? For instance, in the previous example, what if instead of 200 watts you had installed 500 watts? Well, in simple terms, it is possible. Any excess you produce is sent to the grid. Whether or not the grid operator pays you back for this excess depends on the net metering related policy of the electric utility you are connected to. If your grid operator pays you back for every watt of PV power you pump into the grid, it might look beneficial to oversize your PV system. But then the decision would depend on the system cost and the expected system yields, which in turn depend on the irradiance of the place, module level effects, etc., etc. Thus, there could be quite some optimization that could be done purely at an economical level. So you have now looked at the grid-connected PV system. In the next block, we shall look at some specific kinds of PV system. See you in the next block. Welcome back. So far, you have seen the main PV system topologies, the design rules and some examples of specific PV systems. We shall now discuss the PV system economics and environmental considerations. I shall first start with the basic ideas involved in discussing the economics of PV systems. The economics in the field of photovoltaics can be discussed at several levels, like at the levels of the consumer, manufacturers, PV installers, or technology level, while compared to other sources at grid scale. In this block, I would mainly discuss the economics at technology level. At the consumer level, however, I would briefly touch upon the idea of payback period. What is the payback period? The payback period in finance is simply defined as the length of time required to recover the cost of an investment. So how can this be translated at the consumer level, when a homeowner installs rooftop PV system and expects the system to pay itself back? In the case of a PV system user, the initial investment in terms of system cost is recovered over the years as the PV system offsets the electricity bills. We can understand this idea in a simple example. Let's say, for instance, Family Smith has installed a PV system of 1 kilowatt peak at an initial investment cost of 4,000 euros. The family's usual electricity consumption is such that on an average it incurs an electricity bill of 2,000 euros per year. After installation of the PV system, roughly 800 euros worth of electricity consumed by the family is provided for by the PV system. In this graph, we see a straight line denoting the fixed investment costs in the beginning. As the family consumes more of the clean power produced by the PV system, it offsets the electricity bill accordingly. In this example, the amount saved is 800 euros per year. In other words, the family earns a return of 800 euros per year on the PV investment. As the years progress, the savings accumulate, and there comes a point in time when the accumulated savings are greater than the original investment. The period of time elapsed until that point is called the payback period. In this case, Family Smith's PV system has a payback period of 5 years. Note that the payback period depends on the location of implementation of the PV system. Of course, the sunnier the location, the greater the PV yield and the faster the payback. Also, the savings by the PV system not only depends on PV yield, but also the grid electricity costs. Finally, the initial PV system costs are also a major factor in deciding the payback period. Note that this calculation can become more complex as more parameters are factored in. For instance, if you are considering a significant period of time, usually it's a practice to also take into account the time value of money. That is, for example, 1,000 euros today will have a different buying power 10 years from now. Then there are also policy-based factors. For example, subsidies and feed-in tariffs can affect the initial investment and savings. Let us briefly discuss the concept of feed-in tariffs in PV systems. At the consumer level, feed-in tariff is the rate at which a consumer is paid for the electricity that the grid-connected PV system contributes to the local grid. There could be two kinds of feed-in tariffs, gross and net. Gross feed-in tariffs are paid for all the electricity the panels produce, irrespective of the domestic electricity consumption of the consumers. Net feed-in tariffs promise a higher rate for the surplus electricity fed into the grid after domestic use of the consumers is subtracted. Now we must not confuse the payback period of the PV system with the energy payback time, which is a different concept, and I shall discuss this in the next block with the environmental considerations. Now, let us go to the concept of levelized cost of electricity, or LCOE. It is the cost per kilowatt hour of electricity produced by a power generation project. It is usually used to compare the lifetime costs of projects based on various power sources. The concept of levelized cost of electricity allocates the cost of an energy plant across its useful lifetime to give an effective price per kilowatt hour. It is similar to averaging the upfront cost of the production over a long period of time. The levelized cost of electricity calculation could get very complex depending on the various parameters considered. In the simplest of terms, if we know the annual PV yield for the system over its lifetime and the accompanying system cost, the levelized cost of electricity can be found out as shown by this formula. Here, AT is the total annual cost in year, T. I0 is the initial investment, and ET is the annual energy yield or electricity. R is the discount rate, which is a factor used to discount future costs and translating them into present value. Based on the side of the PV generation and the cost of materials, the levelized cost of electricity of the PV project could vary a lot. Also, the discount rates used for evaluation will have an impact on the levelized cost of electricity value. For the power producer, the levelized cost of electricity is a valuable indicator of the cost competitiveness of a certain energy technology. It is also a good price point indicator, that is, the power producer will have to sell the power at a price greater than the levelized cost of electricity to make profit. Of course, the policy structured around PV energy, like feed-in tariffs, subsidies, and other incentives, will all play a role in determining the grid power prices. Finally, we come to the much popular term grid parity. Grid parity is the situation at which the PV power can be generated at a levelized cost that is equal to the power price from the conventional electric grid. This could be generalized to other renewable energy technologies as well. But there is one significant difference between PV and other renewable technologies like wind turbines or hydro dams. Compared to these other sources like wind turbines or hydro dams, PV can be scaled down to the level of a single module. This means that the PV power is now effectively competing with the retail grid price, which conventionally includes other costs like transmission, distribution, etc. Therefore, compared to wholesale price, PV grid parity for retail grid prices can be reached faster, as shown in the graph. The graph is depicting the volume of PV implementation on the x-axis, which can be directly correlated with time, as the past decade has seen the implemented PV volume rise tremendously. As capital costs decline with increasing volumes, PV power is expected to be cheaper. On the other hand, cost of fossil fuels due to the availability and emission cost are expected to rise, thereby increasing the conventional grid costs. Also, as discussed before, the solar levelized cost will depend also on the site location, as sites having more sun hours will having a lower levelized cost of electricity. Grid parity occurs when the solar and grid lines in the graph cross. Of course, the grid parity could be reached faster with the help of incentives and subsidies. However, a school of thought disregards such a grid parity that has occurred with the aid of subsidies. It is said that the true grid parity is when the PV power prices would fall below the grid prices without any subsidies. Solar grid parity without subsidies is a much rarer phenomenon, at least right now. As an example, PV power producers already claimed true grid parity in the sunny country of Spain earlier in the year. The grid parity is a very important indicator of the usefulness of a renewable energy technology. The closer a technology is to the grid parity, the easier is its integration in the energy mix of the region. With the advancement in technology and the maturity of manufacturing processes, grid parity for solar is expected to be a more popular occurrence in several places around the world. I hope you now have a better idea of the economics involved around the field of photovoltaics. In the next block, we will focus on environmental considerations for PV systems. See you in the next block. Welcome back. After looking at the economics of the PV systems, we will now look at the environmental considerations surrounding the PV systems. Why look at the environmental considerations at all? Well, one of the most important reasons for looking at solar as an alternative source of energy was to harness the clean energy from the sun. That is, we wanted to mitigate the energy shortage in the world in a cleaner way. So we should also ensure that the process of building these PV generators and system doesn't undo the good that they do in their usual lifetimes. But how exactly do we quantify the environmental impact of the PV systems? How do we measure if they are having a positive impact in their lifetimes? There are multiple ways of doing this. A lot of people try to measure the carbon footprint or the carbon emissions caused due to the manufacturing of the PV panels and then compare with the carbon emissions offset by the panels during their lifetimes. Another, more analytical approach is to look at the total energy spent in the manufacturing of the various PV panels or systems. Different manufacturing processes have different energy needs, and these are then compared with the clean energy produced by the PV systems over their lifetimes. Some experts also try to do a complete life cycle analysis, trying to trace the energy and carbon footprint of the PV panels throughout their lives, or as in more commonly known, from their cradle to grave. For the sake of this video, I shall cover the energy-based approach. I will first introduce some basic terms that are related to this approach. Let's start with the energy yield ratio. The energy yield ratio is nothing but the ratio of the total amount of energy yield of the PV system to the total amount of energy invested in its lifetime. As the PV yield depends on several factors like the size of the PV system, quality of the panels, the technology choice, etc., etc., it is possible to see a wide range of energy yield ratios when observed in practice. PV modules can have this ratio as large as 10 to 15, while PV systems will usually have smaller energy yield ratios. Now let's go to the energy payback time. It is defined as the total energy input over the lifetime to the annual energy yield of the system. Note that this shouldn't be confused with the system's economic payback period. Usually, the energy payback period of most systems is anywhere between 1 to 7 years, depending on the equivalent sun hours available in the place of implementation. Let's take a look at some of the PV technologies and how they fare in terms of the amount of energy required in their manufacturing. As there can be a considerable variance in the manufacturing processes, the graph shows the range of primary energy use for PV module manufacturing. As can be seen, the thin film technologies like amorphous silicon cost much less energy to be produced compared to the monocrystalline silicon, which can easily consume around 12,000 up to 18,000 kilowatt hours per kilowatt peak. Note that these numbers are often changing and would only read better as the manufacturing technology improves and the processes become more energy efficient. You must remember that the energy spent in the manufacture of the entire PV system would be more than required for the PV modules. However, it is difficult to allocate the exact energy cost to balance of system components like batteries and inverters, mainly because the technologies and manufacturing processes for balance of system might vary a lot across the variety of products available. Even so, there have been studies carried out to estimate the energy requirements of the whole PV system. In general, it is found that the energy need for the balance of systems is significantly lesser compared to the PV module manufacturing, depending on the PV technology and the balance of systems. The graph here shows the energy payback time for PV systems based on two different PV technologies, polycrystalline and thin film amorphous silicon. Also, the time taken to pay back the energy invested in manufacturing the PV module, the module frame, and the balance of system is shown. It can be seen how regions of higher irradiance show a lesser energy payback time than the PV systems in the low irradiance areas. It can be seen that the module's energy payback time is smaller than that of the entire system. Thin film amorphous technology based PV panels pay themselves back faster in terms of energy due to their low energy manufacturing process. However, the balance of system for the PV system based on the same technology have a larger payback time, owing to lower yield of the amorphous silicon panels. In general, the energy payback time across technology and irradiance levels is seen to be between 2 to 6 years. I would like to remind you again that these fascinating differences in PV technologies can also affect the design choices at the system level, just like we had seen in week 7 in the modules block. The thin film amorphous silicon panels can work better under diffuse light. The crystalline silicon panels are more efficient, but amorphous silicon panels are less power intensive while manufacturing. So we see again that a lot of optimization is required at the system level to choose the optimal module depending on several factors. In summary, it can be seen how the energy payback time is much lesser than the PV module's lifetimes, which can be as high as 25 to 30 years. For the system discussed in the previous graph, the energy yield ratio are also anywhere between 4 and 10. Thus it can be said that the energy invested in the PV system manufacturer is payback several times over during its lifetime. So we can conclusively debunk the myth that solar panels consume more energy to be produced than they generate throughout their lifetimes. Also, the European Union already has in place several recycling directives that have led to recycle practices in place for the large amount of crystalline silicon panels being used. There are studies that even indicate that up to 80% reduction in the production energy of the panel. This would further reduce the energy payback times of the crystalline silicon panels. Thus it can be said that the PV systems are beyond doubt net energy positive in their lifetime. So you have now seen the economic aspects and the environmental considerations of the PV systems. I hope you are now as convinced as I am that solar is the energy source of the future. Now, we only have one video left. In the final video, I will summarize the lessons we have learned in the last 8 weeks. I will share with you my final thoughts on solar energy. See you back in the last block. Dear solar energy students, we have arrived at the end of the course. You have been introduced to a wide range of topics which cover the various technologies which try to harvest the energy in the light coming from the sun. Let's look at a short overview of the important things you have learned. In the first week, we have discussed that the current energy infrastructure heavily depends on fossil fuels. Fossil fuels are mainly used for energy conversion into heat, mechanical energy, or electricity. Solar energy is an alternative, sustainable route converting the energy in sunlight into heat, solar fuels, or electricity. The photovoltaic approach, which converts solar energy directly into electricity using semiconductor-based devices, has been an important part of this course. I've discussed that the effective installed solar power is the fastest increasing power generation technology in the world. If we extrapolate the trend of the last 5 years, the contribution of solar energy to the electricity generation could be on the same level as nuclear and hydro energy before the end of this decade. The forces behind this fast growth are the decentralized character of domestic PV systems combined with the grid parity achieved in many countries. Soon, PV installations around the world will break through the magic level of a 1% contribution to the worldwide electricity production. We started the theoretical part of this course by discussing the spectral shape and irradiance of sunlight. The spectrum of the sunlight incident on the Earth's surface is determined by the temperature of the sun and the absorption, scattering and reflection losses in the Earth's atmosphere. You now understand that the spectral shape basically determines the potentially achievable conversion efficiencies of the various semiconductor materials when used in a single junction device. In weeks 2 and 3, we have discussed the physical fundamentals of photovoltaic technology. We have discussed various properties of semiconductor materials, such as the valence and conduction band, its band gap, and the transport mechanism of the charge carriers, like drift and diffusion. We have discussed the working principle of PN junctions. These junctions separate the light-excited minority charge carriers. In week 3, we saw that the behavior of the solar cells can be explained in terms of the external parameters: open circuit voltage, the short circuit current density, the fill factor, the maximum power point, and the conversion efficiency. In addition, we have discussed the design rules of solar cells and categorized them in terms of spectral utilization, utilization of the bandgap energy, and light management. These are handy tools to understand the differences between the various PV technologies. In weeks 4 and 5, we have looked at the various PV technologies. As example, we have discussed the 3 crystalline silicon wafer-based solar cell with the highest achieved conversion efficiencies up to date, like the Pearl solar cell, the interdigitated back contacted solar cell, and the heterojunction-based solar cells. You have seen the various silicon processing methods to make electronic-grade silicon and multicrystalline and monocrystalline wafers. We have quickly touched upon the various other PV technologies, like 3-5 semiconductor multi-junctions, the cadmium telluride PV technology, the CIGS PV technology, the thin film silicon technology, and the organic-based PV technologies. Every PV technology has its own advantages, such as the high conversion efficiencies, abundantly available source materials, low cost price per watt peak, the possibility to process it on flexible substrate, etc., etc. In week 6, we have looked to alternative energy conversion approaches using solar energy. We have looked to the welcome technology of using solar energy to heat water and concentrated power approaches using heat engines to make, again, electricity. We addressed the challenge for any sustainable energy technology in the future, which is the ability to store the generated energy. In that light, we shortly talked about a combination of photoelectrochemical and photovoltaic approaches to convert solar energy in fuels like hydrogen and methane. In week 7, we looked at the crucial components besides the PV module that make a PV system, like inverters, charge controllers, maximum power point trackers, and batteries. In week 8, we have discussed the design rules of both a standalone PV system and a grid-connected PV system. The economic and environmental aspects have been looked into in more detail. Arriving at this final point in the course, you can be proud of yourself. You have learned and mastered a broad range of topics related to solar energy technology. Be aware that this course has the function of being an introduction. If you are interested, fascinated, and inspired by the various topics addressed, you can find many books and scientific literature that tackle the various topics in more depth. Several universities around the world offer education focused on solar energy technologies. For example, at Delft University of Technology, we have a PV profile in our master's program, including courses like PV Basics, PV Technology, PV Systems, and the PV Lab course. After this final lecture, you will find the final exam. After you have finished your exam, I would like to ask you a last favor. Could you make a short video, not longer than 2 minutes, in which you talk about your solar energy system? If you don't have a system, make a short movie where you interview your neighbor, your friend, or your relative who has a PV system. Upload your movie on YouTube and share the link with us in the dedicated discussion blog on the Solar Energy edX platform. We can learn from other people's experience and inspire each other. As examples, I will upload some homemade movies myself of people talking about their PV or solar thermal system. Finally, we arrive at the end of my lecture. I personally would like to thank everybody from the edX and DelftX team who helped us making this massive open online course. This time, I can't finish with saying, see you in the next block. Therefore, I would like to close with the words, I hope to see you and your learned skills back in helping solar energy to become an important and sustainable contributor to humankind's energy needs.